Die Sprachübertragung beginnt jetzt. Alle Teilnehmer befinden sich im Zuhörermodus.
Dear ladies and gentlemen, welcome to this web demonstration. The topic today is e-mobility. My name is Ilja Tsikur. I'm senior engineer at KISSsoft AG. And you will also find below in the web meeting tool a place where you can ask questions. Beside me sits Dr. Michael Stangl. So he will try to answer your questions live. And in case some of the questions are not answered, then we will do it afterwards after the web demonstration. In addition, in the web meeting tool, you will find some material, for example, the presentation that I'm going to be using. I'm also going to use some KISSsoft models, and these are going to be published on our homepage along with this web demonstration in a few days after we have recorded it. And there you will also have the option to download the KISSsoft files in case you want to play around a bit with the software and with these models that I'm going to show you. Okay, so I think we are ready to start. So the first thing I'm going to talk to you about are different gearbox concepts within the e-mobility. And we're going to speak about different possibilities in KISSsoft that are used for gear sizing, gear optimization, sizing of grinding allowance, of tools, and so on. And at the end, I'm also going to speak about a little bit about manufacturing. So what aspects should be maybe considered when we grind gears. And I'm going to also speak about some possibilities that Gleason can offer you in terms of metrology and gear measurement, and also the estimation of the transmission error, which is very important for noise. So first of all, on this slide, you will see different types of gearbox concepts. They are all created in KISSsoft. And you can see maybe a standard configuration here on the left side. This is a two-stage cylindrical gearbox. You will see later on in a short calculation example that if we want to have, let's say if our optimal motor speed is about 6,000 RPM and we want our vehicle speed to be about 80 kilometers per hour at this motor speed, then for such a gearbox, we would require a gear ratio of, let's say, of about 8 to 9. But there are also different ways we can realize this. On the right side, you see something that was originally developed by Gleason. This is a high reduction hypoid. The speciality about it is that you have a very low number of teeth on the hypoid pinion, and this allows you actually to get very high gear ratios for a very compact size. On the low left corner, you see a solution with helical gears and a hypoid gear, so like a combination of those two. In the middle, you see a realization with planetary and hypoid gears. And maybe this one particular on the right side is also interesting because sometimes you may want to recuperate energy, and the optimal gear ratio for recuperation and when you're driving the car may be different. So this is actually a shifting gearbox with the possibility to shift from recuperation to drive mode. Here is a typical calculation example. We are actually going to work a bit on this example today, where you see a input electric motor. It has a certain power, 80 kilowatts. We have an input speed of about 6,000 RPM. We want to have two stages in this example, and the customer says that they want at this particular motor speed a vehicle speed of 80 kilometers per hour, and this at a wheel diameter of 632 millimeters approximately. Here we have some additional input data, which is, let's say, common. We have some minimum safety factors for root and flank, also for the shaft, dynamic and static safeties. We have some requested service life, of course, in hours. This is not only for the bearings, but for the entire system, if we talk about gearbox reliability in general. We have some materials here that we can use. It's a case-hardened steel. Housing is out of aluminium, so rather lightweight. So here is actually a very simple formula with which I can estimate the required gearbox ratio. So if I have now a motor speed times diameter times pi divided by the desired vehicle speed, then I can actually calculate the gear ratio. And if you see, if I enter this into the formula, I get a gear ratio of about, let's say, 8.9. So since I have two stages, I have to divide it. So I have chosen in this example to have a gear ratio of 2.3 on the first stage and a gear ratio of 3.7 for the second stage. So the first thing we do actually when we start designing this kind of gearbox, we actually have to model the kinematics. And for that, we have two different tools. I think most of you at least have heard about KISSsoft. Some of you have worked with this tool. But we also have a new product, which we call KISSdesign. And it has this sketcher functionality, which allows me to quite quickly generate such a kinematic model. So I just enter here 4 points. This is going to be my input shaft. Now I will model my intermediate shaft, place an axis, and I will model my output shaft. Just like this. Now I will define gears on these different shafts. So here I will have my pinion. So I add here a cylindrical gear. On the intermediate shaft, we have 2 gears. So one gear over here and another one over here. And on the output shaft, we will have one cylindrical gear. Now I will need some bearings. So I'll start off here. I'll add a bearing on this side, another bearing on that side. I do the same thing for the intermediate shaft. And I do the same thing for the input shaft. Place here 2 bearings between the gear. Now I will need some input and output coupling. So I add here a connection coupling on the input and a connecting coupling on the output. Now I can connect the gears just by dragging one gear on top of the other. And as you can see, this is already now my finished kinematic model. So from now on, I could enter now the load data and so on, and I could start off with gear sizing. So this is a quite efficient way to, let's say, evaluate different gearbox concepts. I'll not save it. Okay, so the next step I want to talk to you about is the rough sizing procedure. Or maybe some additional comments on the whole procedure. We will start off by sizing the center distance and phase width for each individual stage. Then we will have to find out the optimal macro geometry of the meshing. So module, pressure angle, helix angle, and so on. And as you have seen, we have actually a case-hardened gear. So we will probably have some distortions after hardening. So we may as well design a grinding stock for hard finishing process. And part of the result of such a grinding stock is that if we don't grind the root along with the flank, then what we get is a grinding notch in the root area, which is not so good for the mesh, for the gear, for the root safety especially. So we may as well design a cutter which will reduce the effect of such a grinding notch. Then we'll perform the calculation of deformation. And I mean deformation of bearings, deformation of shafts, like bending deformation, and so on. And based on that, we're going to have our system inclination, system deformation, and this will influence our contact pattern. So in order to optimize the contact pattern along the face width, we will then design different types of flank line modifications. I will say a bit more when we get there. After our contact pattern is optimized, we can actually start talking about noise and vibration optimization, which we do with the tool called contact analysis, which actually also calculates the meshing under load. So we consider the deformation of each individual tooth. And based on this analysis, we can then size profile modifications. And once we've done that, we can export some manufacturing and metrology data for further steps for manufacturing and measurement. Okay, so what is the idea of rough sizing? The idea is, as I said, to fix basically the gearbox main dimensions like center distance and tooth width, which of course influence then the housing parameters. As input, we have torque, or if you want, power. We have some nominal speed. We have a gear ratio for each individual stage, material quality, and of course the required safety factors that we need to achieve and required service life. This depends a bit on the application, and it's of course also very company specific. So the standards actually don't tell you how these safety factors should be chosen. They just give you a method to calculate them. Now, in the fine sizing procedure, we can have different targets. So one target would be we find center distance and phase width in such a way that we, for example, want to minimize the weight or have a low size or maximize the torque capacity, or even better, maximize the power density, which I will speak to you a bit later when we have done that. So for this first calculation, you see I have prepared a small KISSsoft model. It's basically just the kinematics. You can see that we have no center distances yet fixed. The gear ratio is 1:1 on each gear. This is why we have some shafts within another shaft. But so this is how I would start off modeling gears. So I have prepared, let's say, simple shaft geometries so that we can actually calculate some deformations and also perform some sizing procedures. So I will now go to the first gear stage. Now you can see this is our standard interface for the cylindrical gear calculation. You see we have here no gear ratio currently. And now I'm entering the rough sizing procedure. If I would have center distances already fixed, for example, if I have a housing that is already manufactured, I would actually then enter here the center distances, and that way KISSsoft would only generate solutions for this particular center distance. But in our case, the center distance will be a design parameter. So I'll just enter here a nominal gear ratio. I suppress integer ratios. Then another important thing is here the option, the area of use of gears. Actually, I want to use own inputs. As you know, industrial gears and automotive gears don't actually look really much the same. So this is why we have here the option to set a ratio of face width to center distance, a lower value, and an upper value. Now I can perform the rough sizing procedure. And the first thing you will see is that we have here different ranges for the center distances that we can achieve. So you see we begin with 70 millimeters and the last solution, so with biggest center distance, 110. But I'm interested in particular, on one hand, on the weight of, and by what I mean by weight is, of course, mass of gear 1 plus mass of gear 2. Here we yet don't consider the mass of the housing or shafts and so on. And of course, I would like to have a solution with minimum weight, but on the other hand, I want to have a high safety factors or high torque capacity. And this is why I normally look at this parameter here, which I call power density, because it shows the ratio between the maximum transmittable torque of this solution divided by the weight. So these 6 solutions will have the maximum power density. And at the same time, I want to choose a solution that is rather compact. So this second choice is actually quite a good compromise. High power density and relatively low center distance. So I can just double click on it. I will round up the center distance to, let's say, 87, face width to 31. And that way I have finished my rough sizing for the first stage. The second thing I will do for the second stage, again, I will do this a bit faster. I go to the rough sizing. You remember for the second stage, we had a gear ratio of 3.7. And again, I set here my own input values for the ratios of center distance, of face width to center distance. Press calculate. And again, I will now sort the solutions according to the maximum power density, which are the upper solutions over here. These are the first 5 candidates. And I'm looking now as a compromise, also a solution with a relatively low center distance. I will choose this solution. So we can close it, round up the values, 122. Face width is going to be 27. I will make the face widths equal for both gears. And I can now close this calculation and update my model. So now we can see we still have some collisions. This is why I like KISSsoft, so I can see actually where I can expect some collisions. Right over here, this gear collides with the bearing. So I could as well just go to the intermediate shaft calculation. I will put this gear a bit more to the right side, close the model, and open the output shaft. Here I will move the bearing a bit to the left side. And if I now update my model, you see that we have actually no more collisions that we can expect. So this was rough sizing. The next step is we want to perform fine sizing, which is the optimization of gear macro geometry. What is the basic idea? Well, we go into this procedure with a fixed face width and a fixed center distance. These parameters we do not change anymore. As a result, we expect optimal gear macro geometry, module, pressure angle, helix angle, and so on. And we can also enter as input a module range, pressure angle range, and helix angle range. Maybe we don't want to go too high with the helix angle because of very high resulting axial forces on the bearings. And another thing which is maybe important for e-mobility is that we could also define a target contact ratio. So we want to have actually a higher contact ratio for the gears to make them quiet. Especially we want to have a full integer number of the contact ratio, so that we have basically either all the time 2 or 3 teeth in contact, so that the stiffness variation is lower. Now, you can see we can define also a goal over here. We can say our target is, let's say, as an e-mobility engineer, e-mobility gearbox engineer, I want to have high torque capacity, so higher safety factors. I want to have low weight, low noise excitation, which actually means high contact ratio. And of course, high efficiency. We want to produce efficient gearboxes. Now, here I will show you now two different reference profiles. So basically the shape of the hop. On the left side, you see a standard reference profile according to ISO. This is a standard cutter, but you actually cannot achieve a higher contact ratio, a transverse contact ratio with this profile. If you want to have an integer contact ratio, you should actually modify the tooth shape, and this is called a deep tooth form. So it has a higher basically higher tooth form that gives you a higher contact ratio. So let us do this. I will go back to KISSsoft. We have performed the rough sizing, and now I will open up my first stage, and what I'm going to do is the first stage I'm going to design as a helical gear without the deep tooth form. And the second stage, we're going to make it a deep tooth form so that you can see both examples. So I go to the fine sizing tool for the first stage. See, our nominal gear ratio is already set. And now I can define a range for the module. So let's say I'll go from 1 to 3, and this in, let's say, 0.25 millimeter steps. I could also change the pressure angle, which I will not do in this example. I'm just going to change the helix angle, let's say from 0 to 15 degrees, and this in 3-degree steps. Under conditions number 3, I can say that I want to reject all the solutions that have a lower than required safety factor, and I want to suppress these integer gear ratios just as option so that the software eliminates these solutions in the beginning. So now we press calculate, and you see we found in short time 124 different solutions, but all of these solutions, have a look, they all have the same center distance, same face width. So we're no longer changing these values. Now we can go to the graphics tab, and all these numbers that you see are different solutions from the list clearly. And what I am particularly interested in is the total contact ratio of this meshing. This you will find right over here. What I could do as well is I just could go to the result list and sort all the solution in terms of total contact ratio. And what I'm interested in particular are the solutions that give me really a full number of contact ratio. And this is, you can see it here. Here it's about 3.0. So I could eliminate all the solutions that I don't like. I will delete these one as well. So now I have only solutions that have a full contact ratio of about 3. And now I could continue and say I am also interested in, let's say, the efficiency. So I would rather go for, you see the difference is not much big, but the blue solutions here also provide me a very high efficiency. And you see safety factors are also looking really nice. So I can go to the solution list and take my solution number 54. I'm just going to show you, you can see now in the result window, we have here transverse contact ratio, overlap contact ratio, and in sum, these give me an integer number of the total contact ratio. This is how the meshing looks like, optimized. So this is, let's say, a very standard tooth form. Now we'll do something different for the second stage. I'll go to the second stage and I will fine size it. So I go back to the fine sizing procedure now for the second stage, and let us first define again the step size for the module, let's say from 1.25 to 4 in 0.25 steps. I will also add a helix angle from, well, let's say from 0 to 15, and this in 3-degree step. And now comes the difference. You see, now I can go here and say I want to have a deep tooth form. So this basically means the software will change the reference profile, and I want to have a transverse contact ratio of let's say equal or higher than 2. I will also reject solutions that don't meet the safety requirements, and I'll actually now again run the calculation. Okay. So now what I'm particularly interested in, you can see all the solutions that we have generated have a transverse contact ratio of 2. Now I am looking for a solution that gives me a total contact ratio again of 2. So I can sort the solutions in terms of total contact ratio, and I will just delete all the solutions that don't match this criteria. So right up to here, delete. And you see here we actually have a lower contact ratio than 3. So I'll delete everything else as well. Now all the solutions have a transverse contact ratio of 2 and a overlap contact ratio of 1, which in total again gives me 3. This is something that is really should really gives a very good performance in terms of noise already, even without profile modifications to begin with. Now I could perform the same procedure, look for a solution that has, there is no efficiency more than 1, just all these solutions you see they have about the same efficiency. But we could, for example, now also look at the mass. You can see we can still save about 100 grams of mass. It's not much as we did in rough sizing, but we could still consider that. So I will now choose the solution number 91, which seems to be in the first place a good compromise between low weight and a very good safety and a low noise and vibration excitation. So I go to the list, choose the solution number 90. What was it? 91. I have to sort this list, and there you go. This is the solution number that I'm particularly interested in. So if I now press calculate, you can now see the transverse and overlap contact ratio. Let us have a look at the tooth form. So this is my mesh, and you can actually see that if I now simulate this, we actually get, this is now, of course, in the transverse contact ratio, you can see that at each step we have always 2 teeth in contact, which gives me good behavior of the meshing. So this was fine sizing. I can now again update the model. You can see now that the gear geometries will change. And now you can see this is our new gearbox. That's looking nice. So let us continue. Now, as I said, we need to size the grinding stock if we're planning to grind the gears, and this is actually quite a nice formula to estimate the grinding stock per flank. This formula was provided to us by Gleason. We are collaborating more and more, so we actually really wish to include more manufacturing stuff into KISSsoft also in future. And now you can see that the grinding stock or grinding allowance per flank is depending on the base tangent length allowances, this for soft and final machining as you know it. Then this parameter VE is actually the offset that you get after hardening process. And the profile slope deviation, helix deviation, and pitch deviation, these are quality related parameters. And in the formula, you should also be careful if you apply it. For example, if you do threaded wheel grinding, normally you would use 100% of this total pitch deviation for the estimation of the grinding stock. If you're honing, then normally this value is taking roughly 30 to 60%. And all these values are, of course, in micrometer. Now, if we are a bit unlucky and we do not wish, or we do not have the technology right now to grind the root along. By the way, with threaded wheel grinding today, as per today, you can actually grind the root along with the flank. But for example, if you're honing, then normally it is not done. And also in many cases for threaded wheel grinding, you just don't grind the root along. And you see we get here a grinding notch. And this can, of course, result in higher root stress concentrations within this grinding notch. As you can see here, we have performed a FE calculation on that. So in order to avoid that, we want to design a protuberance cutter. Let us have a look how this protuberance cutter looks like. So here are the parameters that we need to define. And normally this value of the protuberance, which you see here, it is chosen normally slightly bigger than the grinding allowance. Then you need to define Then you need to define the protuberance angle, and we can then calculate the protuberance height automatically. So this I would like to demonstrate again while using our fine-sized model. So first I'll start off with our normal meshing. This was the gear pair 1, 1 and 2. And now I will go to the reference profile tab and say I want to define my own machining stock, which I have calculated by the formula that I've shown you before. And let's say my result is, when I've entered all the values, well, let us enter here 0.05. So 50 microns of grinding stock is at least necessary to compensate the distortions after grinding. So if I now press calculate, you can see what happens. We have here in the root area this grinding notch, and I want to get rid of that. So I will now design the protuberance cutter. I go here to own input, press on the sizing button for the protuberance height coefficient. Now, as I said, I choose the value of the protuberance slightly bigger than the value for the grinding allowance. I will enter here some protuberance angle, maybe typically something between 8 and 15 degrees. I'll just go for 10 degrees, press calculate, accept. And the same thing I actually want to do for the second gear. Here I do the same, 0.052 and a protuberance angle of 10 degrees. Press calculate, accept. So now if we calculate our meshing again, you see we still have a bit of undercut because of the protuberance, so I might as well just optimize it a bit, but I will not do it so detailed in this example. And you can actually see, let me show you this in the graphic manufacturing of gear 1. Here you can actually see that we almost have no grinding notch left here after that. So you could also show this for pre-manufacturing. Let me just go to the settings tab. First, I normally deactivate everything. So let's have a look first on the pre-machining. So this would be our hobbing cutter. You can see how we cut how we basically perform the soft machining with protuberance. And now that we have performed the grinding, which is then here the second step, this is our final tooth shape. So this is how you can quickly and efficiently design the right cutter. Okay. Let us continue. Now we need to calculate the deformations. When we calculate shaft deformation, it is important that we also consider bearing stiffness. Here I'm showing an example of the influence of bearing stiffness on the shaft displacement. And so you see the blue curve would be without bearing stiffness, and the red curve would be if we consider bearing stiffness based on bearing inner geometry in the shaft calculation module. So you would see me as a gear engineer, what I'm interested in is the difference of the bending line on the left and on the right side of the gear. So if I would be lazy and say, yeah, bearings are infinitely stiff, then I could say that I don't need to compensate for anything. This line looks like really straight. But if I add the influence of bearing stiffness, you can actually see that the gear is tilting to the left. And this will, of course, induce uneven load distribution, and this I can expect. Now, here is the definition of the face load factor. It's important to show this because we have a direct link for gear microgeometry on torque capacity. And this is done through the face load factor, and Annex E of the ISO standard actually considers shaft deformation and flank line modifications while it's calculating analytically the face load factor. So what is it? It's basically just the maximum line load divided by the average line load. So ideally, I would love to have a KH beta of around 1. Now, the problem is we never have perfect gears, we never have perfect housings, so we also have some kind of effects from manufacturing errors. On one hand, due to axis non-parallelism, so this is something like, let's say, manufacturing error of the bores of the housing, and we have a total helix slope deviation. This is a gear parameter, which basically shows that my helix angle is not really the one I would like to have after I have considered manufacturing errors. And now we need to actually analyze KH beta for each of these different manufacturing error cases. On one hand for the perfect gear, then plus, plus, minus, minus, and different cross combination of those. So at the end, I'll get 5 KH beta coefficients, and I am of course interested for the worst case, which you would actually see here. This is the line load distribution along the face width. And in this particular example, I have calculated KH beta in the worst case of 2.2. And the ISO says I have to calculate the strength with the worst KH beta coefficient. So now we'll go on to the sizing of flank line modifications. And the procedure is like this. We have our axis misalignment, we calculate KH beta, add some flank line modifications, and then again, with that, calculate KH beta. So this is now shown for the same example that I've shown you before. We have now added a crowning and a helix angle modification, and by that we have managed to reduce KH beta of 1.4. So instead of having 220% more line load, I just now have about 40%, which is already much better. If I would add this into the strength calculation, this would basically result in 45% higher root safety and 20% higher flank safety. So I just want you to digest this. A couple of micrometers of flank line modifications can give you 45%, in worst case, more torque capacity. This is why grinding of gears is so important. So let us do an example on that again. I will open now a different model. I'm going to be using this model over here. And I'm going now for the first stage. And first, I would like to show you in the factors tab, this KH beta is calculated without the shafts. So no shaft deformation is basically directly considered. It is considered indirectly, but not very accurately. If I go now to the ISO Annex E, without manufacturing allowances, I can now calculate my new KH beta. And you see, while it's calculating it, it performs real shaft calculation. And now you can see we have actually 50% overload. So I can also show this to you in the contact analysis tab. This is maybe an important point. I use contact analysis quite a lot to visualize stuff, for example, like the contact pattern and so on. But for the sizing of flank line modifications, you could actually do that just with these ISO standards that I was showing you before. And you wouldn't need to run it because the ISO annex is actually doing it on the pitch circle. And normally, if you know the load distribution on the pitch circle, it's normally enough for sizing of flank line modifications. So let us have a look how the stress is now distributed. And you can see this typical situation where we have actually a bit more load on the left side, which you can see here. If I would scale the graphic a bit differently, I will add here minimum line load of 600, so you can actually see something that the stress is actually going to the left side of the gear. So now what I can do, is I can go to the modifications tab and get some proposals from the software to for the flank line modifications. So I go to the tooth trace modification, I press sizing, and the software will now tell me approximately how many micrometers of flank line modifications I need. If I accept that, if you look at the resulting proposal, this crowning can first of all be actually neglected. It's a very, very small value, but you will see later I will need this value. So I will round up the helix angle modification on both gears to -8 microns. And now I will run the contact analysis again. And we will now see the influence of these modifications on the contact pattern and, of course, on the face load factor KH beta. An important thing to understand is all these axis inclinations that we get due to shaft bending, we compensate with this helix angle modification. Torsion and manufacturing errors are compensated by increasing the crowning. So now we can see we have really very optimal contact pattern with these modifications. And this also results in a KH beta of 1.00, this without manufacturing allowance. Now I did a good job. Now what happens if I do have some manufacturing errors? So I change to calculation with manufacturing allowances. I get some new proposals for the helix slope deviations and axis non-parallelism. This depend on the quality standard, of course. And now I will again perform this calculation. And what you will see is that KH beta will of course increase, and I will try to reduce this KH beta simply by increasing the crowning on both gears. The reason the calculation is now taking a bit longer because it actually has to calculate all these 5 cases that I've been speaking about earlier. And you can see I had a KH beta of 1.5, I optimized it, and I had 1.0. Now I add manufacturing errors, and I was basically now back at where I started. So let us have a look at the phase load distribution, and you can actually see which case gives us the worst KH beta factors. This is the line load now, and these two graphs, you can see the green one is when they are both in plus, and the purple one is the one that is both with minus. So actually, I can't compensate that by adding a helix angle or increasing the helix angle modification, because these errors can go either to the left or to the right. So the only way to cope with that is to actually increase the crowning. And I will do it now. I will increase the crowning to 5 microns on both gears. Now I'll run the analysis again, and I just hope to get more optimistic KH beta coefficient for each individual manufacturing error case, or let's say for the worst case, to be more precise. So now while it's running, I want to show you another thing. It is the manufacturing twist to manufacturing. If we do threaded wheel grinding of helical gears that have a crowning on top, just alone by the kinematics of the grinding machine, we induce a twist. So this would be my optimal modification, but what I get is actually something like this. And we have received from Gleason an approximation formula to actually model this twist, and this option is now also available in KISSsoft. You can see now I have a crowning, and you see I have reduced KH beta to 1.33, and at each possible loading manufacturing error condition, I don't have this edge contact, which is good. I will now change back to just decrease a bit the calculation time. Now I want to show you the effect of the twist. So for that, I need to add here 2 modifications on both gears, and it's the option which is right below in the list, twist to manufacturing. Here as well, twist on both gears. I have this effect because I grind both gears. So I enter here the value of the crowning. And we can now run the contact analysis so that we can see this effect on the contact pattern. So modern grinding machines, especially if you would use a threaded wheel grinding machine, a modern one, normally they have an option to compensate this twist automatically, but in certain applications where you just cannot allow yourself to lose more time during the manufacturing process, you just live with this twist. I'm not saying this is the best option, but we do have some customers who do that. And this estimation of the twist actually allows you to say, yeah, can I live with it or not? And this is the basic idea also of the calculation that we are doing here. So we just wait a few more moments. Maybe while it's calculating, so that I don't waste your time, I will just continue and show you the results later. So yeah, contact analysis. The next step is that we perform a contact analysis under load, which basically considers each single tooth deformation and analyzes the meshing under load for each meshing position. And you can actually see what happens if a tooth deformation takes place. You have here a contact which happens before you have expected, and it ends after you have expected it. And here is actually an impact. So this is something you should always be aware of and apply proper profile modifications to get rid of this effect. So after I have run the contact analysis, what I get are these contact impacts. I've shown this to you for a standard reference profile and for a deep tooth form. We have it for both. And you can see the contact chokes over here, and we can see the transmission error. What is the transmission error? It is a noise and vibration relevant parameter, which basically tells me that how much does my contact point on the path of contact deflect due to the tooth bending. So if you want to have a low noise and vibration excitation, what you want to have is a small amplitude of this signal. And another thing you want to have is a low orders of harmonics. So what is that? If I convert this function or transform this function according to Fourier transformation, what I get is a sum of sine and cosine waves, and a pure sine wave would mean that I would have only one dominant order of harmonics. If I have a lot of orders of harmonics, that means that my signal is really not very smooth. So this can also be influenced by profile modifications. You can actually see how much better we are with a deep tooth form. This is here a deep tooth form. Without profile modifications, we get already quite a nice signal and a very low amplitude. By the way, these scales are the same, so you can really compare these two signals for a standard profile and a deep tooth form. Now we start modifying our gears. So we add profile modifications, which you can see here. We can select the amount of profile modifications, which mainly influences the path of contact, so to eliminate the contact shock. And in addition, you can see that we get a much smoother signal of the transmission error for the standard reference profile and for the deep tooth form. This is almost like a straight line. So I would really expect very low noise excitation from this kind of meshing. So how do we manufacture these profile modifications? So this is now more a bit in the direction of manufacturing. What you can see here is one of the Gleason newest machines, 260GX. This machine can also work in closed loop, so it can grind your gears, then send the data to metrology system, and then send back the result to compensate for the error. So you can actually achieve very high qualities. And the profile modification themselves, they are included into this dressing wheel that you see here below. The flank line modifications are generated through machine kinematics, so they're not part of this geometry here. They just you induce them by special machine kinematics. And the twist due to manufacturing that I will show you now quickly can be also compensated. So I have finished here the calculation. I just wanted to show you the influence of the twist. So we have here stress distribution on the tooth, and this is basically what you get. So you can see here that we're losing contact, and now you have to decide as an engineer, can you live with that or not? Should you invest time to compensate for this twist? We have actually the same graphics in 3D so that you can actually really see the stress values and so on. All right, so this was the influence of the twist. Now, how about if we talk about honing? So honing is a different, let's say it's an alternative for the grinding, for threaded wheel grinding process. When is honing often applied? In case you have maybe some kind of special geometries where you have shoulders. So if you think of this gear right here, you wouldn't come with this threaded wheel grinder on the lower gear over here. So you actually would need to hone this kind of meshing. And here the things are actually quite similar. So you have, instead of the dressing wheel, you have a dressing gear, which you can see here, and the profile modifications are added here on top. The flank line modifications are generated through machine kinematics. They also say that the surface structure, surface waviness that is generated by honing is more, let's say, more advantageous in terms of noise and vibration. So this is a lot of automobile manufacturers are actually, they actually prefer to hone. Not all of them, but a lot of them. Another alternative to manufacture gears that have, let's say, geometric constraints, let's say like shoulders and so on, would be power skiving. Gleason offers solutions to perform soft power skiving and hard power skiving as an alternative to the processes that I've mentioned before. And you can see that we can also produce these profile and flank line modifications quite easily. They are just integrated into the process. In KISSsoft, we have a new option to actually assess the manufacturability with power skiving. Well, what does it mean? In KISSsoft, you have designed your gear, you can enter some shoulders, some diameters, and so on, and the software will actually make a preliminary check if this meshing can be manufactured by power skiving method. In future, we are also planning to do this for honing, but this is just, I can't promise to you yet, but we're working in this direction as well. Another nice thing is that we can size the number of tool teeth and perform, as I said, first collision detection, and we can also simulate that for external, but also for internal gearings, which you can actually see here. This is a very effective process, especially if you have complex geometries. Now I come to the last part. This is the manufacturing and metrology. So how do we transfer KISSsoft data? Well, on one hand, we get these manufacturing drawings from KISSsoft directly. Here you can see the flank line diagrams for both left and right flank. This here is the profile diagram as well, and we have some basic macro geometry data provided here to you as a summary. An alternative, or let's say a more efficient way to export the data for manufacturing is to use this GDE export. This is basically a machine language, which, let's say, modern machines, I think I could say so, modern machines actually accept this format. You could also transfer this data to the hobbing machine or to the grinding machine or even to the measurement machine. An alternative for that would be to use a measurement grid. And in KISSsoft, we have the option to generate a measurement grid, which you can actually see here, which divides the whole gearing into a grid. And you can see here all these parameters for measurement for each individual point of the grid. This is for measurement in particular. Gamma software and metrology. This is, I think, a very important topic, especially if noise and vibration is a topic for you. On one hand, we calculate this transmission error in KISSsoft. Not this, but the parameter transmission error in KISSsoft. This calculation is based on a loaded tooth contact analysis. So basically, it really calculates the transmission error based on tooth deformation. But what if we ask the same questions on how well is my gear manufactured? How is my surface of the gear? And this is what Gleason does. You can see we have here a GMSL machine. It's actually a laser measurement machine. And here you can see the topology of the flank measured by laser. Here you can also see the results in classical diagrams, and based on that, based on the non-perfectness of a gear with the Gamma software, we can actually calculate the transmission error that we can expect in load-free situation. So now you can think together with me. I believe that the future is that we can superpose the results that we get from KISSsoft based on deformation, superpose them with a measured gear, add them somehow on top, and then get very realistic results of what you get later on in terms of transmission error and harmonics on the real gear. This is, I think, something that we would like to follow this direction in future. And with this, you will also find some references here in my presentation. Maybe you're interested to read that. I would like to say a big thank you for your attention. I hope you liked that. And we will still stay here for a couple of minutes just to answer maybe some open questions. Thank you very much for your attention and have a nice day.